Alrighty. And then, so this session is going to be recorded so that if you need to come back later, or you maybe missed out on today's event, you'll be able to come back and watch it. So at this time, we ask that you please mute your mics for the best sound experience. Otherwise, the feedback could interfere with the information we'll be sharing with you today. So without further ado, here is Mr. Albert Azasi.
Hello, everyone. Yes, I'm going to go over the 0324 and 1324. Let me share my screen so you guys can see my PowerPoint. Okay, let me see here. Share screen. Let me go there. Okay, now today's topic, I'm going to cover, I believe this is chapter 8, concept of chapter 8 and chapter 9. Okay, so these are, all the topics that I'm going to cover today: sets, subsets, proper subsets, operation on sets, intersection of two sets, union of two sets, disjointed sets, Venn diagrams, introduction to probabilities, basic concepts of probabilities, multiplication principles, permutations and combinations. These are like two workshops combined into one. So this workshop might go a little bit over 1 hour. Okay, so start off sets. For the first few slides, there's a lot of definitions that you have to be aware of. Okay, for example, sets. A set is a well-defined collection of objects.
I'm sorry, Mr. Azasi, we don't see your screen.
Okay, hold on. Let me go back. Okay, let me see here. Okay, now, okay. Can you see it now?
Yes, sir. Yes, sir. I see it.
Okay, let me go get it real quick. Here we go. I'm sorry about that, guys. Okay. Slideshow from the beginning. So like I mentioned earlier, these are the topics that I'm going to cover. Okay, all these right here. There's about 10 to 12 topics. And this is from chapter 8 and chapter 9 on 1324. So the first topic that I'm going to cover is sets. Like I mentioned earlier, that there's a lot of definitions on the first few slides that you need to know or need to be aware of. A set is a well-defined collection of objects. Examples of sets. Well-defined collection of objects means like one, all the students in my math class. I like to use these examples when I teach sports face-to-face. Number two, letters of, in the alphabet, all these are well-defined collection of objects. The collection of young adults, this is not well-defined because how do you define young adults? How can I make this a set is by adding the age. For example, the collection of young adults between the age of 18 to 29, now it's well-defined. Okay, now sets are denoted by capital letters. Like I say, capital letters such as A, B, C are used to name sets. Each object in a set is called a member or an element of the set. And the brackets or braces are used to enclose objects in a set. For example, this is set A equals to the elements 3, 4, and 5. And this is what it means again. Set A consists of elements 3, 4, and 5. The symbol, this symbol means is an element of the set. And the symbol here with a line over it means it's not an element of the set. For example, the set A is equal to the elements of 3, 4, and 5. So 3 is an element of set A, right? Or 3 is an element of 3, 4, 5 because 3, 4, 5 is set A. So these are the same thing right here, these two. And here's how you will say it in words. 3 is an element of set A, or 3 is an element of the set containing 3, 4, and 5. 2 is not an element of A, or 2 is not an element of the set 3, 4, 5 because 2 is not in here inside set A. So this is also the notation for that. And here again is the explanation. 2 is not an element of set A, or 2 is not an element of the set containing 3, 4, and 5. Now sets definition and examples. Empty set. An empty set has no elements. There's two different notations for an empty set. For example, like the zero or the O with a slash over it, or the braces with nothing in there. These are the same thing. This means empty set. Equal sets. Equal sets contain exactly the same elements. So in other words, two sets are equal if they contain exactly the same elements and the order is not important. For example, these are equal sets. The set of 3, 4, 5 is the same thing as or equal to the set of 5, 4, 3 is equal to the set of 4, 3, 5. These are all equal sets. Sometimes we describe a set by coming property of its elements rather than by a list of elements. Up to this point, these are all lists of sets. Now, there's a property that is called a set builder notation. For example, this is how you read the set builder notation. It reads the set about elements X such that X has a property of P. Okay, let me show you an example. For example, okay, here's my set. The set right is those braces. About elements X means that X right there, this X here, the first X, and the slash means such that. And there's X has a property of P. I mean, whatever the set is looking for. Okay, now let's do an example. Example, list the elements in the given set. X such that X is a natural number more than 5 and less than 8. Here, this is something that we should know, okay, at this level. What are natural numbers? A natural number is the same thing as a counting number. A natural number starts with 1 and they go all the way to infinity. And whole numbers start with 0 and go all the way to infinity. So for example, here, this will be X is a natural number more than 5, right? So can it be 5? No, right? Because it says more than 5. And so it's going to be 6 and 7 because 8 is not included because it says less than 8. So the answer is a set 6 and 7. On B, X such that X is an integer and is between -3 and 1. If you notice here, the -3 is not included because it doesn't have that slash on the bottom, which means that greater than or equal to. So for example, -3 is not included, and the 1's included because it has less than or equal to 1. The symbol here. So the answer here will be what -2, -1, 0, and 1. Okay. And again, this is what you need to know, what I just explained about natural numbers and whole numbers. Whole numbers start with 0 and they go all the way to infinity. And counting numbers start with 1 and they go all the way to infinity. Natural numbers are counting numbers. At times they say natural numbers and at times they might say counting numbers. So this is something that you guys need to know. Okay, now here, state whether the statement is true or false. So for example, number 1 states 3 is an element of the set containing the elements 2, 5, 7, 9, and 10. Is this true or false? What do you guys think? Anybody? You can just put it in the chat. Very good, it's false, right? Because 3 is not an element of the set 2, 5, 7, 9, 10. So in other words, 3 is not inside the set here. So that's false. And there's the explanation. Number 2, 2 is an element of the set containing the elements 2, 5, 7, 9, and 10. This is actually true. Why? Because 2 is inside the set here. 6 is not an element of the set 1, 3, 5, 7, 9. That's also true, right? Because 6 is not in here, in the set here. 6 is not an element of the set. 4 is not an element of the set containing 2, 4, 6, and 8. This is false, right? Because 4, it is in here. So that's false. 4 is an element of the set. The set with elements 1, 2, 3, 4 is equal to the set with elements 4, 2, 3, 1. This is true, correct? Because they have the same, they have the same elements on both sets. So this is true. The set containing A, B, and C is equal to the set containing the elements A, B, C, and D. This is false, right? Because it's missing the D on the first set. That's false because it's missing the D, the element D. Number 7, the set all the whole numbers greater than 5 and less than 9 is equal to 6, 7, 9. I mean 6, 7, 8. Let's see the greater than 5, right? So 5 cannot be included, so it's true, and less than 9, so this is true. And that's the explanation. Greater than 5 and less than 9 means the whole numbers between 5 and 9. All the natural numbers not greater than 4. Okay, so no more than 4, right? So my bad, guys. I went too quick there. So it's 0, 1, 2, 3, right? So this is false. Why? Because 0 is not a natural number. Okay, now number 9. The set x such that x is an even integer from 5 to 19, and 5 and 19 are included. So everything between 5 and 19, that's even. So it's 6, 8, 10, 12, 14, 16. Is this true or false? Anybody on the chat? Right, very good. It's missing the 18. 18 is missing on the set. Number 10, the set such that x is a vowel. Are all these vowels? A, E, I, O, U. So this is true, right? Those are all the vowels. Okay, now let's continue. Here are more definitions here. Subsets and proper subsets. First of all, what's a universal set? A set that contains all the objects being discussed. When when I teach this course, I tell my students, my class is a universal set because nobody else can be included, just Mr. Isasi's class. So that's the set being considered. That's an example of a universal set. Subsets and proper subsets. Here's a definition from the book. Set A is a subset of set B written. This notation here, guys, means subset. Okay, A is a subset of B, provided that every element of A is also in B. So in other words, for A to be a subset of B, everything in A must be in B. I mean, or every element or member has to be on B. Set A is a proper subset of set B. Okay, this is the symbol for proper subset. If every element of A is an element of B, but B contains at least one element that is not in A. So in other words, every element in A, right, is also in B, but B contains more elements that are not in A. That's what it means. It can be one or it can be more. When set A contains an element that is not in set B, then A is not a subset of B, and we write it as A is not a subset of B. Okay, this is the notation. This is my okay. Now, for any set A, because the empty set is always a proper subset of any set. And also the empty set is also a subset of any set. And a set is a subset of itself. Okay, and that's important because we're going to do some examples pertaining to this definition here. Examples. Here we have set A equals to the elements or members that have A, B, and C. Set B is equal to has the elements A, B, C, and D. And set C has elements C, A, B. Okay, let's see here. Okay, now, let me go back here. Okay, guys, these are the examples, guys, so you guys can go over them, okay? For example, A is a subset of B, which means every element in A is also in B. A is a proper subset of B, which means every element of A is an element of B, but B contains at least one element that is not in A, right, which is D. You see all these elements here are also in B, but B contains the element that's not in A. That's what it means by B here. On C, every element, I says B is not a proper subset of A. Every element of B, right? Every element here in B is not in A, right? Because B doesn't have the D. So this is that's how you read this right here. Okay, now how about D? A is a subset of C, which means every element in A, right, is also in C. All right, or this can be equal subsets, right? I mean equal sets, right? Because every element in A is also in B. And remember this definition here? I'll say a subset of itself. So for example, this is set A, right? Set A is A, B, and C. and set C has exactly the same elements. So we can say, so this rule can apply because C is equal to A. Okay, now let's do, where are we at? Let's go here. Okay, let me go back. Hold on. Okay, here we go. We're actually on E. A is not a proper subset of C. Let me see here. A is A, B, and C is C, A, B, right? So these are equal, right? Equal sets also. But you know what, guys? Remember the definition of a proper subset? That every element of A is an element of B, but B contains at least one element that's not in A. So the set A and C contain the same elements. C does not contain an extra element that's not in A, so that's why this is not a proper subset. And F, the empty set is a proper subset of A, and that's true because from the definition here, the empty set is a proper subset, and the empty set is a subset of any set. Okay, now, I believe here, guys, there was a mistake in the book because I got these from the book. Okay, I believe this should have been not this is proper subset and this is not a subset. So I believe it should have been just also proper subset, either a proper subset or not a proper subset. But I copied it just exactly the way the book was, so that way it can help you with some of the examples or some of the homework. Okay. So for example, from 11 to 19, you'd have to put place the proper subset or not a subset. Okay, so let's see. They give us A. Set A contains the elements -4, 0, and 4. Set B contains the elements from -3 all the way to 3, right? Or the integers from -3 to 3. Set C contains -4, -1, 0, and 4. Set D contains 0. Set E contains -4, and this is my universal set. The universal set, or set U, contains -4, -3, -2, -1, 0, 1, 2, and 3, and 4. So then on number 11, so it's either A is a proper subset of U, or A is not a subset of U. Which one can be true here? All right. So would it be this one here? Because every element in A is also in the universal set. Okay. Okay, now how about number 12? Let's see. E is -4. The set with the elements -4, and A has -4, 0, and 4. So this will be the notation for this one because E, because it cannot be this one here. The proper subset, because every element in E is not in A. So this is the correct choice. E is not a subset. Let's see again here. Where's E? Oh no, this is true. This is a proper subset. Yeah, because E is -4, right? And every element in E is also in element A. In set A. Okay, now I was thinking about this one here. A, right? Set A is -4, 0, and 4, and set E is -4, right? Right now I was thinking about this one earlier, guys. So every element in A is not in E. So this one, not a subset, will be the correct choice. Okay. Every element of A is not in E. Elements 0, 4 are not in E. And here, guys, I put here the explanation. So when students actually go through this PowerPoint, they actually know the reason why. Okay, let's do number 14. Yes, here is B, and here is C. If we notice, all the elements in B are not in C. So here, this not a subset will be the correct choice. And every element of B is not in C. Elements -3, -2, and 1, 2, and 3 are not in C. Number 15. Remember number 15, guys, from the definition that I told you that this was important. Every empty set is a subset or a proper subset of any set. So the proper subset symbol goes in here. The empty set is a subset and proper subset of any set. Let's do number 16. The set containing the elements 0 and 1, let's see, D, is D, right? So this will be not a subset because 0 and 1 are not all in D, which is just 0. So this will be my correct choice, which will be not a subset. If the element of the set is not an element, is not in D. Element 1 is not in D. How about if it's reversed, right? If it's reversed, this is D, well, because it's first. So D has the element of 0. And 0, it is on the set elements containing 0 and 1. So this is a proper subset. And there's the explanation. Every element of D is an element of set 0 and 1, but set 0 and 1 contains at least one element that's not in E. Number 18, let's go look at D and look at B. Right? So every element in B, right, which is G0, is also an element in B. So this will be a proper subset. Okay, and just I just went over the explanation. Now let's see A and C, right? So we look at A and we look at C. A contains -4. It's also in C. 0 is also in C. And 4 is also in C. So this will be a proper subset. Again, every element of A is an element of C, but C contains at least one element, not in A. And again, guys, I got this from the book. And that's where the instructions, what you do, guys, but I believe they did a mistake. It should have been not the bar in the bottom. Or it should have been a proper subset or not a proper subset. Okay, that's what I think, okay? But anyway, that's exactly from the homework from the book. Okay, now these are subsets, okay? List all the possible subsets for each of the given sets. Let's first, I'm gonna start with A. And recall, set A is a subset of set B, wherein A is a subset of B, provided that every element of A is also an element of B. Okay. So here's my solution, okay? So we always start with the empty set, right? The empty set is always a subset of any set. Now, let's take a specific order. Let's start with one element at a time, okay? So 4 is a subset of the set 4, 6. And also 6 is a subset of the set 4 and 6. And then, right, there's no more single elements, so now let's do both elements. So the set 4 and 6 is a subset of the set 4 and 6. So how many are there? There's 1, 2, 3, 4, right? So there's 4. So there's 4 subsets. If you have 2 elements, a set with 2 elements has 4 subsets. Okay, right now, guys, it's going to lead to the definition of the set within elements is equal to 2 to the something power. Okay, and that's going to help you with some other homework also. Now set B. Again, let's start with the empty set. Right, so the empty set is a subset of the set A, B, and C. Now let's start to keep some kind of order. Let's list them with a single element. Right, so A is a subset of the set A, B, and C. And then B is a subset of the set A, B, and C. And then we do C, right? And then that's all the possible combinations with only one element. Now let's try with 2 elements. So let's try A and B is a subset of A, B, and C. Now let's try A and C is a subset of A, B, and C. And now let's try B and C. It's a subset of the set A, B, and C. So that's all the possible combinations, right, with 2 elements. Now comes with 3 elements, and a set is always a subset of itself, right? So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. So a set with 3 elements has 8 subsets, right? So here's the definition. A set of n distinct elements has 2 to the n subsets. So for example here, right? How many elements were there? So 2. So 2 to the 2 squared is equal to 4. And over here, it was what? It was 1, 2. It was 8, right? So 2 to the 3rd power, because there were 3. 2 to the 3rd power is equal to 8. That's how we use the definition. But here, guys, they want you to list them. So if they say to list them, you have to do it in this format, like this, like A, and B, and C. But if they want you to find the number of subsets, they don't want you to list them. They want you to find them, right? So for 20, it's going to be 1 element, so it'll be 2 to the 1st power, which is equal to 2 subsets. Number 21, right, we have 1, 2, 3. So it's going to be 2 to the 3rd power, which is equal to 8 subsets. Number 22, the set X, right, set X is a whole number less than 5. Remember the whole numbers? The whole number is 0, 1, 2, 3, and 4, right? whole numbers less than 5. So it's going to be 1, 2, 3, 4, 5 elements. So 2 to the 5th power equals 32. So there's 32 different subsets. It will be kind of hard to list all the subsets that has like 4 or 5 elements, because it's going to confuse you with all the different the different ways it can be. For example, with 3 it's going to confuse you, right? Because we have we'll start with one element. With the empty set, then one element, then 2, then 3, and so forth. Imagine with 5 or 6 elements, it's going to be kind of hard to get list all the possible combinations. But for the definition, guys, here all they want you to do is just number them, not list them. Okay, now here comes operation on sets. Given a set A and a universal set U, the set of elements of the universal set that do not belong to A is called the complement. The complement of A is written as A complement, or read as A prime. I like to say not A. This little like a little wiggly line on top, or like the comma on top, right? A means prime, or I like to say not A. Okay, it makes more sense when you say not A. Okay, let me show you the example. The universal set of U equal to 1, 2, 3, 4, 5, 6, all the way to 12, right? And set A is 1, 2, 3, 4. So let me show you in a Venn diagram. Okay, so this is the universal set, right? Nothing else included, only what's inside here, this box. This is set A, this is A, and this is not A. How do we write it? How do we put all the elements inside a Venn diagram? Okay, so we need to find the A complement, or A prime, or I like to say not A. So not A means not 1, right? Not 1, because set A was 1, 2, 3, 4, right? So not A means not 1, not 2, not 3, and not 4. So what's left? 5 through 12. That's the complement of A, or not A. Okay. So now how do we write it in the Venn diagram? This is my universal set. This is set A, right? So set A contains 1, 2, 3, 4. So 1, 2, 3, 4 must be inside the circle here. There's 1, there's 2, there's 3, and there's 4. So not A must be outside the circle, right? So you can put them anywhere you want, but they cannot be inside the circle, and also they cannot be outside here, guys, right? Because all this is a universal set inside the box. So that's how you draw your Venn diagram. Okay. Now, intersection of two sets. Are you guys okay up to this point? Does anybody have any questions? Okay. So given two sets, set A and B, the set of elements belonging to both set A and B is called the intersection of two sets written A intersects B. At times, guys, it's kind of, for some reason, students don't understand that about intersection and AND. So this is my wording for them, right? So this is the correct verbiage in math. You have to say intersection or the word AND. But at times when students do not comprehend that, I like to say elements belonging to both sets, or what do they have in common? This is my verbiage here, what I like to say. What do they have in common? This is also from the book, belonging to both sets, but I like to say, what do they have in common? At times when I mention this, what do they have in common? I believe it makes more sense to some of the students that they have a hard time understanding the math vocabulary. For example, the universal set B is 1 through 12, right? And set A is 1, 2, 3, 4, and set B is 2, 4, 6, 8. So so this symbol here, guys, is important, right? That means AND or intersection, or elements belonging to both sets, or like how I say to students, what do they have in common? So they have in common 2, right? And a 4, right? Or you can say elements belonging to both sets, 2 and 4. So that's your set. So the set A intersects B is equal to the set containing the elements 2 and 4. Okay, now, how do we put that into a Venn diagram? Right, this is U, stands for the universal set. Everything is included inside the box. There's my set. This will be my set A. This will be my set B. So intersection will be right here, right, where both sets intersect. Okay, that's like the concept here. But how do we write it? Do we write this situation in the Venn diagram? There's my universal set. So what's in set A? I mean, you always start where they intersect, right? So where do they intersect? 2 and 4. So 2 and 4 goes here first. 2 and 4. And then set A contains 1, 2, 3, 4, right? So 2 and 4 are already inside here. So 1 goes. So my set A will be 1 and 3, right? Because 2 and 4 are already here. So the key thing here, guys, is to always start where they intersect. And then you get the elements of set A, and then you get the elements of set B. So for set B, right? So we have 2 and 4. So what's missing will be 6 and 8. Now, what elements, right? Because this is my universal set, is from 1 through 12. What elements are not in set A and B, right? So all these elements, the ones that are not in both of these sets, they have to go here outside the circles of A and B. So for example, 1 is not in there. There's 6. 7 is missing, so 7 goes in the outside. 7, 8 is there already. 9, 10, 11, and 12. That's how you do this problem into a Venn diagram. Okay, what are disjointed sets? Disjointed sets are sets that do not intersect. Okay, for any set A and C, if A and C are disjointed sets, then A does not A and C. A intersects C is an empty set, which means they don't cross or they don't intersect. Here's an example of what I'm saying here. What do they have in common? Right? Nothing in common. A and C have nothing in common. So it's an empty set. So this is how you put it into a Venn diagram, right? So that's it. U, the universal set. That's set A and set C. This is called disjointed sets. Okay, now, so how do we write it? I mean, how do we express this in a Venn diagram? So set A is 1, 2, 3, 4, which will be, this is set A, 1, 2, 3, 4. And set C will be 5, 7, 9, 11. And the rest of the universal set has to be outside the two circles. We got 1, 2, 3, 4, 5, 6 is missing. 7's here. 8 is missing, so 8 goes in the outside. 9 is there. 10 is missing. 11 is there, and 12 is in the outside. That's how you express this problem in a Venn diagram. Okay, now the OR. The OR means union. A or B means union, right? And this is my symbol. This is how I like to say it, guys. Again, because some of the students don't comprehend the math language here. So I just tell them, list all the elements of both sets, but do not repeat. That's what I tell them to do. List all the elements of both sets, but don't repeat them. So I would tell them just write everything in set A, and then go to set B, and if the elements are already there, don't put it again. Okay. For example, again, it's the same set A, and here we have set A is 1, 2, 3, 4, and set B is 2, 4, 6, 8. So to find A or B, or A union B, I started with set A, right? Set A is 1, 2, 3, 4, right? 1, 2, 3, 4. Then I go to set B. Is 2 already there? Yes, right? So I don't put it again. Is 4 there? Yes. So I don't, put it in again. Is 6 here? No. So that's why I put the 6. Is 8 here? No. So I'm going to put down the 8. That's how you express the A union B or A or B. Okay, now there's how to express it in a Venn diagram. So you always start where they intersect, right? The union means everything in both sides. It means all this right here, everything here. So you can add everything here. What's in A, what's in A intersects B, and also what's in B. Okay. So again, we're going to start with set A. We're going to start always. We can do this, right? But I would rather prefer to start here, guys, and then take it from there. But anyway, there's 1, right? The 2 and the 4 is what they have in common, so those go there. And then for set B, right, we have 6 and 8. 2 is already there, 4 is already there, so 6 goes here, and also the 8 goes there. And the rest of the numbers that are not in A and B go in the outside of the circles or set A and B. Okay. Now all this, guys, is leading to what's coming up next. Okay. This is just like the definition that I copy and pasted from the book. That's what it means by not A. If this is A, this is not A, shaded in blue. The intersections of A and B, right, is what they have in common. It's this portion here. And how you read it is a set with elements X such that X is an element of A and X is an element of B, right, which means where they intersect. And for the union, A union B equals to the set of X such that X is an element of A or X is an element of B or both. And that's what it means, right? That's the union. Okay, now, everything that we've done so far is going to lead to problems 23, 24, 25, 26, 27, 28. And I also got these from the book. Okay, because most of the times when an instructor assigns homework on MyMathLab, they don't give you, they give you something similar, but they don't give you the same problems as the book. But it's very, very similar. So that's why I decided to assign you these, because most right now, since the courses are online, most instructors they give the homework and exams through MyMathLab for this course here. Okay. So before I start, guys, I like to do this, right, because we have to find the complement of x, y, right, of x and y. So I like to start doing this. So this is my set x, right? Is A, B, 1, 2, 3, and not x. Right, you're going to go to your universal set. So it's going to be not A, not B, right? And then not 1, 2, and 3. So whatever's left is what's complement of X or not X. Same thing with right set Y. Set Y is B, D, 1, 3, 5. So the complement of Y or not Y, right, is not B, not D, not 1, not 3, not 5 from the universal set. So not B, not D, not 1, 3, and 5. So A, C, E, 2, 4 are left. So Z is B, 2, and 3. Since I'm not doing the complement of Z here, I don't use the complement of Z. So number 23. Okay, let me go back a little bit. Where X intersects Y, or X and B, they'll say X and B, right? So what do X and Y have in common, or where do they intersect? We go to X and Y, right? So let's see here. Do they both have a B? Yes, right? So B is my first element. How about a 1? Yes. How about a 2? No. How about a 3? Yes. So that's my answer for 23. Now for 24, right? Like I mentioned earlier, the easiest way is to write everything in set X, right? So we're going to put X here first. We're going to put A, B, 1, 2, 3, right, from set X. Now we go to set Y. And if it's already in there, you don't write it again. You don't repeat it. So let's go to set Y. Is B there? Yes. How about D? No. So we're going to put D. How about 1? It's already in there. How about 3? It's already in there. How about 5? No. So that's my result. Okay. Not X, it's already, so that's my answer, right? And most of the times the book wants you to put them in order, but you don't have to, right? Because these are equal sets. So the order doesn't matter. But the answers in the back of the book, they put them in order from A to Z and and the numbers, right, from least to greatest. But if you would put this on MyMathLab, it will kind of right, because they're the same thing. Now, not X, guys, right? So not X is already right there, my answer over here. So that's the answer. That's not X or the complement of X. Okay, now the complement of X intersects the complement of Y. So we look at these two here. So let's see here. What do they have in common? Do they have in common C? Yes, it's going to be C, right? C is my first element. How about D? How about E? Yes, E is in there. How about 4? Yes, 4 is also in there. And 5? No, so that's my result. Okay, now, let's see here. Number 27. the complement of x intersects z. So it's going to be these two here, guys, right? Complement of x and z right here. So first, we're going to put everything, like I said earlier, what they have in common. Let's see here. Do they both have a c? No, right? How about a d? No. How about an e? No. A 4? No. A 5? No. So the answer will just be an empty set. Or you can write it with a symbol with a 0 or the O with a slash over it. Okay, for 28, we have to follow the order of operations, right, which is PEMDAS. So first, we're going to do parentheses. So X union, right? So for X union, Y intersects Z. Okay, we go to Y here on top, Y and Z, right? Intersection, what do they have in common? They have in common a B, right? Let's do it here. They have in common a B. D, no. How about a 1? No, a 3. Just B and 3. So that's Y intersects Z. So now, right, so that goes here. So now we start with union now, right? Remember the union? We're going to put everything in X first and set X. You see X is A, B, 1, 2, 3. And then we go to the intersection, who was B and 3, right? Is B already there? Yes, it is. Is 3 already in here? Yes, it is. So this is my answer. The set X will be my answer. Okay. Okay, now. Now, there's Venn diagrams with 3 sets. Okay, from the Venn diagram, list the universal set. I want you to list the universal set U, set A, set B, set C, and the intersection of A and B, intersection of A and C, intersection of B and C, and where they all intersect. Okay, so let's start first with the universal set. So you have A, B, C, D, E, F, G, right? So it's going to be A through G. Now set A. It has A, D, E, G. Set B. Let's call this set B. Let's call this B here. Set B has B, D, G, and F, or B, D, F, G. And set C is going to have C, E, F, G. Okay, now, okay, so we're done with these right here. Now, intersection between A and B, right? What does A and B have in common? Wouldn't it be these two here, D and G? So the intersection of A and B is what A and B have in common, or where do they intersect, which is this portion here. So the answer will be D and G. Now A intersects C, right? So now A intersects C, so it's going to be this portion here. So A intersects C is going to be E and G. And then the set B intersects C, right? So B and C intersect, so it's going to be this portion here. So it's going to be FG. Now where they all intersect, right, is going to be right here at the middle, guys, right there. It's going to be G. And this is very important when they're going to give you some, like for example, right now on the next problem, they're going to give you like a whole bunch of like a scenario. So here's where you always start. You work backwards. Okay, you start here. Okay, let me show you what I mean. Okay, on number 30. Here's number 30. So you have to do A, use a Venn diagram to illustrate the service results. And B, they're going to be asking you questions from B, C, and D. But first, you have to draw yourself the Venn diagram. Okay, let's start it then. So you start, right, by doing the Venn diagram. And how many people are there? There's 60, right? So U equals 60. That's my universal set. Okay, like I mentioned earlier, guys, you always start where all 3 intersect, right? So let C be comedies, right? So this is C, and then let D be dramas. That's D. And let S be science fiction. So this has to be my S over here. Okay. So here, guys, here in red is where you start. I mean, this was not in red in the book. Okay, this is also from the book, number 30. But I put it in red just to signify where you start. So where do they all intersect? Which is this portion here. So this is going to be 6 right here. Okay, that's where you start, and it's equal to 6, which is this right here. Then 13 people like comedies and dramas, right? So we're looking for comedies intersect dramas, right? Because the word and. So C and D intersect, right? Wouldn't it be right here? So this portion here, but 6 already there, so then 7 is missing. That way, these two here must be 13. Now, what's next? 10 people like comedies and science fiction, so comedies and science fiction will be this portion here. So it's going to be 10, right? So if this is 6, this has to be 4 right there. Now we're doing 11 people like dramas and science fiction. So dramas and science fiction, right? So it's going to be this portion here. This has to be 11. So that's 6. This has to be 5. If you start any other way, guys, you're going to get the wrong result. So you always start here where they intersect, where they all three intersect, and then you choose 2 of them. Where 2 intersect. All right. So it's going to be 3 of them, and then you go to the actual set, right? So set C has 26 surveys, right? So you can add all these, right? So 4 plus 6 plus 7 plus whatever is here is equal to 26. So the answer is going to be 9, right? Because 4 plus 6 is 10. 10 plus 7 is 17. So 26 minus 17 will give you 9. Now dramas is 21, right? So all these have to be 21 here. So we have what, 11 and 7 is 18. So the answer is going to be 3, because 21 minus 18 is 3. 25 people like science fiction, right? So all this has to be science fiction. So science fiction is 25, right? So we add 4 plus 6 is 10 plus 5 is 15. So 25 minus 15. So the answer is 10. Now that's the answer. I don't know. It's not the answer for part A, because we have to find out how many people didn't like none of the movies. So we can add all these right here, right? So X equals this is what's not the people that didn't like none of the movies. So we're gonna add all these and subtract that from 60. Okay. So we have 9 plus 7 plus 6 plus 4 plus 3 plus 5 plus 10, which is 44. So 60 minus 44 is 16. So 16 didn't like none of the movies. Now with all this information, you get to answer the A, B, C, and D. So this is the answer for part A. Okay, now for B. How many people surveyed like comedies, right? So we go to comedies, like comedies. So we're looking at this portion here. But neither dramas nor science fiction, right? So they only like comedies. So the answer will just be 9, right? Because it says neither science fiction nor drama. So the answer will just be 9. That's your answer. Okay, now for C. How many people surveyed like dramas and science fiction, but not comedies? So again, how many people are surveyed like dramas and science fiction? So they like dramas and science fiction, but not comedies. Let's see here. So it's going to be, let's see, how many people surveyed like dramas. And so how many like these 2, right? But not comedies. So this will be my answer, guys. So it's going to be 10 plus 5 plus 3, which is 18. Only these right here. Okay. And I jumped the gun. Number D was how many people like none of the movie styles. So the answer was 16, guys. So it's always good to draw yourself a Venn diagram, because it's kind of easier because most of us are visual. So by doing a Venn diagram will assist you in understanding what they're asking for. Hey guys, that's let's see here. Now comes 8.2, which is probabilities. Okay. Okay, now let's see here. So we have to know what random experiment is, sample space. The random experiment is a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. Sample space denoted by S is a set of all possible outcomes of the random experiment. So for example, right, if you flip a coin, what can it be, right? It can be, the sample space is either heads or tails. So it's going to be either H or T, right? H for heads and T for tails. Rolling a fair die. A fair die guy means that the die is not what's it called? Is not fixed, because at times it's loaded to one side, and when you roll it, it always goes to the same number. Okay, that means that is not fair. But a fair die has 1, 2, 3, 4, 5, and 6 on it because it's a cube. So to find the sample space of an experiment, at times it's easier to draw a tree diagram. Here's an example of a tree diagram. Find the sample space of flipping a coin twice, right? So here's flipping a coin. That's once. It can be heads or it can be tails, right? This is one flip. By next flip, if it was heads first, it can be heads or it can be tails again. And then if it was tails first on my first flip, then it can be tails heads or tails tails. So this is my sample space. It's going to be heads heads or heads tails, right? Or tails heads or tails tails. So that's my sample space. Heads heads, heads tails, tails heads, and tails tails. Okay, now an event. An event is an outcome, or as I said, outcomes of random experiment. An event is a subset of the sample space. Okay, let me show you what it means here. So for example, if a sample space for flipping a coin is S equals to H heads tails, right? Then one event can be heads, which represents the outcomes of heads. Okay. Checkpoint. This is from the book. Suppose the die is tossed. Write the events in said notation. The number showing is less than 3. Okay, so solution, the number showing is less than 3, right? So this is my sample space, and the number showing is less than 3 is going to be what? 2 and 1, or 1 and 2, right? For B, the number showing is 5, so the answer will just be 5. For C, the number showing is 8. Can it be an 8? No, so it's going to be the empty set. The die shows an even number. So how many are even? 2, 4, 6. So it's going to be 2, 4, 6. Okay. Okay, now, this is the basic probability principle. P of E stands for the probability of the event to take place, equals to the number of the event over the number of the sample space. Okay. This is like what we're going to be using right now. The definition, the probability of an event is a number that indicates relatively likelihood of the event. Okay. N of E is the number of elements in the event, N of S is the number of elements in the sample space, right? Or I mean, that's what the N stands for, the number. Checkpoint. Suppose a single fair die is rolled with a sample space 1, 2, 3, 4, 5, 6, right? Given the probability of each of the given events. So for A, the die shows an even number. Right, so the die shows an even number. So this is the probability of the event, right? So it's 3. So it's going to be 3 elements, right? And what's my sample space? It's 6. So the probability of the event will be 3 over 6, which is equal to 1/2. The die shows a number less than 10. So less than 10 includes all 6, right? 1, 2, 3, 4, 5, 6. So it's going to be 6 elements. And again, my sample space will be 6 because there's 6 ways it can be. So it's going to be 6 over 6, which is equal to 1, which is 100%. The die shows an 8, right? So there's no elements that have an 8. So it's going to be 0 over 6, which there's no way you can get an 8. That's how we do the probabilities. Okay, now. Also, guys, a single playing card. I know I'm going to pass a little bit, guys. I'm going to try to see if I can hurry up. But I believe this is important here, guys. So I'm going to see if I can finish it. Hopefully, I won't go too long. Checkpoint. A single playing card is drawn at random from an ordinary 52 dart deck. Find the probability of drawing a queen. And that's for part A. B is a diamond. C is a red card. And D is a face card or an ace. When I teach this course on face-to-face, guys, I like to bring, when I'm doing this section, I like to bring cards. I like to bring dice to class. And then that way it's visual. So I was thinking, how can I make that into the PowerPoint here, guys, right? So this is what I came up with. And these are just, went online and I got these pictures from there. Okay, so playing cards, there's 52 cards. These are called clubs. These are called spades. These are called hearts. And these are called diamonds. If you notice, the ace can be like a 1, right? You have ace, and then you have 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have a jack, a queen, a king. You have the same cards, but different suits. For every suit. So then there's going to be 52 total cards, right? So there's going to be 26 black cards, right? The clubs and spades are blacks. There's going to be 26 red cards, which are the hearts and the diamonds. And now there's what are face cards? Face cards are the ones that show a face. right? So every suit has 3 face cards, which is the Jack, Queen, and King. So they're all here, right? So there's going to be a total of, right? There's going to be there's going to be 12 face cards. So for example, a Queen, right? So the probability of a Queen, right? There's 52. 52 will be your sample space. For all these. A Queen, how many queens are there? There's 4 queens, right? Because there's 1 queen, for each suit. So there's 4. What's my sample space? How many cards are there? 52. So 4 over 52 will equal, right? Reduce it to 1 over 13. This is the answer, 1 over 13. For B part, a diamond. How many are there? There's 13 diamonds, right? So 13 divided by the sample space, which is 52. So 13 over 52, right? Then we reduce it. So it's going to be about 1/4. A red card. A red card are going to be 26 cards, right? Because the red cards are all the hearts and all the diamonds. So 26 over the sample space, which is 52, right? So it's going to be 1/2. A face card or an ace. Okay. So how many face cards are there? Right? There's going to be 12 face cards. And how many aces? 4 aces. So what the or means, right? So it'll be 12 plus 4. So over the sample space, which is 52, so it'll be 16 over 52, which reduces to 4 over 13. So this is my answer in green. Okay, now, basic concepts of probabilities. This this is a roulette turntable from Vegas or other casinos. So we're going to be using the addition rule for probabilities. For any event E and F from a sample space S. So the probability of E union F or the probability of E or F equals to the probability of E for the probability of F minus the probability of E intersects F. So here's my solution, guys, okay? So let's say example 1, when playing American roulette, the copier or the attendant spins a marble that lands on one of the 38 slots in a revolving turntable. The slots are numbered 1 through 36 with 2 additional slots labeled 0 and 00 that are painted green, right? Here they are. So half of the remaining slots are colored red and half are black. In the roulette, the slots labeled 00 are not considered even or odd. Find the probability that the marble will land on a red or an even. So here's how people kind of bet in Vegas, right? So they wonder, so what's the chance for it to be a red or even on the spin? So let's do this. So I went all the way across, guys. All the way across, and I counted all the red ones, right? It was 1, 3, and so forth, right? So all these are red. So then the rest are black. The blacks are the ones that are not here. Okay. No, this is a set of that's a set of even BE, right? So these are all the even ones because they're asking for even or red, right? So RB the red and EB for the even. So now, so we're looking for red or even, right? That's a key word. So we're looking for union. So how many are red, right? Wasn't it? There's 18 total red. There's 18 black. There's 18 even, and there's 18 odd. So here, right, so we want red and even, right? This is supposed to be red. This is supposed to be even, guys. Let me see if anybody did marble with that on a red or an even. Hey, guys, this is wrong here, guys. This is supposed to be all right. Or, and, oh, no, hold on, guys. Red and even, right? Red and even, the number, okay, we're looking for this right here. Red and even, right, for the intersect. It's going to be 8. Why is it 8? We're looking for this part first. Why is it 8? Because red and even have 8 in common. Hold on, guys. Let me check on my battery running low. Let me see here. Okay, now. So probability of the event, right? So let's do this. So the probability of red or even, we know that red intersects even are here, right? We have, let's see, even 1, 2, 3, 4, 5, 6, 7, 8. That's where the 8 comes from. So we're looking for this part here, right? So we have probability of red. There's 18 red. Probability of even will be 18. minus, right, for the red and the even intersect, and there was 8. And I just mentioned them. They were here, right? They were the 12, the 14, 16, 18. That's 4, and the 30, 32, 34, and 36. So there's going to be 8 minus 8 over 38. So the answer will be 28 over 38, guys. So that's the probability that's going to be red or even. And you reduce it to 14 over 19. So here, guys, what I did here, I put all the information there was total at 38. There's red, black, red, even. Red, 18 red, 18 black, 18 even, 18 odd. And here's what red and even intersect, right? Which is this part here for the formula, which was 8. And I just mentioned how they got the 8. We plug them into the formula and we get our result. Okay, now example 2, let's see here. Suppose 2 fair dice are rolled. Find each of the given probabilities. The first die shows a 2, or the sum of the result is 6 or 7. Okay, so here's my solution. So for part A, we're going to use the same formula again. Let A represent the event that the first die shows a 2, right? So A is the first die shows a 2. Let B represent the event, the sum is 6 or 7. So here I drew a picture of all the possible combination dice. So again, so A union B, right? Or where it says here the die shows, the first die shows a 2, or the sum is, right? Or means union, when the sum is 6 or 7. So first we go here, right? How many have a 2? The first a 2, 1, 2, 3, so it's going to be 6, right? First of all, my sample space is 36. There's going to be 6, right, for event A, because the first die is a 2. And then 11, right, for B, because this is when you add them, right, it's 6 or 7, right? These are all 6, which is 1, 2, 3, 4, 5. And this is 7. These are all the combinations can be 7. So 6, 1, 5, 2, 3, 4, 3, 3, 4, 2, 5, and 6, 1. And we add them, it's going to be 11. And let's see here, right? So it's going to be 6 over 36 plus 11 over 36. And where do they intersect? Right here. So it's going to be minus 2, 4, and 2, 5, right? So there's 2 of them. So that's what's going to be minus 2 over 36. So the answer will be 6 plus 11 is what? 17 minus 2 is 15. Then we reduce it. The answer is 5 over 12. The sum is 11, or the second die shows a 5. Okay, so for part B, the sum is 11. Again, the sample space is 36, so the sum is 11. So we're going to let A be the sum is 11. Right, so the sum is 11, so there's only going to be 2, right? The sum is 11, so it's only going to be 2. And for B, the second die shows a 5. So, right, this is my second die here, guys, right? So it's going to be all these right here. So it's going to be 6. Now, where do they intersect? Will just be this portion here, which is only 1. We plug them into the formula. So the P of A, which represents the sum is 11, was 2, right? Because it's only these 2 here. 2 over 36 plus let B represent the second die is 5, right? So it was all these right here, so it's only going to be 6. So it's going to be plus 6 over 36, and then minus where they intersect, which was where the yellow circle is. So the answer will be 7 over 36. It's always good to have this at your disposal, guys. For the students, because at times when they try to, and I believe, for my classes, I actually give you guys like this is already printed on the notes. But if you don't have no notes with this drawing here, actually go to the book and it's there, because it's easier to do it with the actual picture. Complement rule. The complement of P is equal to 1 minus the probability of E, and the probability of E is equal to 1 minus the complement of the event E. Odds, the odds in favor. The odds in favor is the probability of E over the probability of not E, or the complement of E. Okay. Observation. So we start, right? So this is the probability of the event to happen, right? is equal to N of E over N of S, right? Because this is a probability of E over the probability of not E, or the complement of E. If you notice, right, this will be the probability or the number of E over the number of the sample space, right? So this is division. So this, you invert it, right? So these cancel, or that cancels to 1. So you're left with the probability of E over the probability of not E, or the number of E over the number of not E. This is easier. Okay. So this is equal to that, and I just proved it to you by using basic mathematics. So this is number 27 from page 434. Our marble is drawn from a box containing 3 yellow, 4 white, 4 blue. Find the odds in favor in drawing a given marble. So for A, right? So we have 3 yellow, 4 blue, and 8 white. The odds in favor in yellow, right? But by using what we learned over here, right? Yellow and not yellow. So how many are yellow? 3, right? 3 are yellow. Now yellow is 4 plus 8. So what's my answer? 3 over 12, which is equal to 1/4. And they want it in this form. This means 1, 2, 4. These two are equivalent. Okay. That's how they do it in Vegas. The odds in favor over the odds not in favor. The odds in favor in drawing the blue, right? So blue is 8, so it's going to be 8 over 3 plus 4. Blue, right, and not blue. So the answer is 8 over 7, or 8 to 7. The odds in favor in drawing a white, right? So it will be white and not white. So how many are white will be 4. How many are not white will be 3 plus 8. So the answer is 4 over 11, or 4 to 11. So most students like to do it this way, right? By the observation. And again, first I proved it to you guys with math. So instead of doing all this work here, just put not the event, the number of not the event, and the number of the event over the number of not in the event. That's what I use here. Okay, now this is also from the book. Okay, exercise 47 to 54, page 435. The data from 2016 General Social Survey can allow us to estimate how many hours people who classify their work status as part-time, full-time, actually worked in the last week. Use the following table to find the probabilities of the events. So solution, right? So my sample space will be 5091, 1,591. Okay. So now full-time workers. So we go to full-time workers. So how many are full-time workers? There'll be 1271. So 1271 over 1591, right? So put it into the calculator, and most of the time you're going to round up to four digits, 4 decimal places. So it's going to be 0.7989. Number 48, part-time workers, right? So same concept. Part-time workers, where the part-time workers is 320, right? Over the sample space. Use your calculator, so it's going to be approximate 0.2011. Number 49, work 50 hours or more. So let's see here, right? So 50 hours or more will be this portion here. So it's going to be what, 393, right? We go down here. So 393 over the sample space. Use your calculator, so it'll be 0.470 approximately. Let's see, number 50. Work 0 to 19 hours. So 0 to 19 hours, right? So it's going to be, what, 106 over the sample space. And then use your calculator, so it's going to give you something like approximate 0.0666. Here, guys, I'm going to do 2 more. I think I'm going to do, 51 and 53. Okay. So again, this is from the last slide. Number 51. Part-time workers, right? So we look at the part-time workers right here. And someone who works 40 hours or more, right? So this means intersection, right? That's a keyword right there, intersection. Part-time workers and work 40 hours or more will be 49 plus 21, right? 49 plus 21, these two here. over the sample space, which will give you 70 over 1591, right? Over the sample space, which will give us approximately 0.0440. Number 54, these two here, guys, I believe are the hardest ones, okay? Because the or means, right, union. So how are we going to do that one? The or means union. So by applying the formula here, okay, part-time workers or someone who worked 20 hours or less. So, right, so part-time workers, so we're looking about these right here. Okay. From the part-time workers, how many worked 20 hours or less? So it's going to be these right here, right? So it's going to be these two. So here we let the PIV is going to be 320, right? 320, right? Because these are part-time workers plus these two here, right? Because they work 20 hours or less, which are these two here. And then minus these because you don't add them again, right? That's why it's minus 77 plus 87. Or you can do it this way, right? You go to 320, and then you don't count these again because you already counted them here. So you do these two here, or you can do it that way. This is more visual, but using the formula, this is how you do it. And again, they represent the part-timers, right? So A is a part-timers, is going to be 320. And B represent 29 hours or less, so it's going to be these two here, right? 29 hours or less. So it'll be 320, right? So 106 plus 129 are these, right? I mean, are the ones here which work 29 hours or less, because this is 9, right? Or it can be all the way to 0. And then minus the 77 and 87 because they were already counted right here with a 320. And that's why this is your answer, guys. 391 over 1591. At times, students actually do it this way. They say, right, so part-timers, they look at 320. So then they looked at 29 hours or less, so they're going to look at these two here. But these two, they already counted them. So that's why they only count 320 plus 29 plus 42. That's another way to do it. But this is using the formula. Okay. Hey guys, we're almost done, I think, in about another 5 minutes, okay? So this is a multiplication principle. This is number 24 from page 477. Suppose n choices must be made. So choice 1, right? And M2 makes choice 2 all the way to choice n. Then there are, you multiply every choice. Different ways to make the entire sequence of choices. Example, how many different heating cooling units are possible if a homeowner has 3 choices for the efficiency rating, 3 options from the fan speed, and 6 options from the air condenser? So by using the definition here, right? So number of choices of efficiency, right? So number of choices is going to be 3. Number of the efficiency of the fan speed, right? We're here with the fan speed, so it's going to be 3. And air condensers is going to be 6. So by applying the property here, all we do is multiply them, which will be 54. 3 times 3 times 6. 54 different units are possible. Okay, now this is number 28. The United States Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are no restrictions on the digits used? How many will be if the first digit could not be a 0? So here, guys, they're asking 2 different questions. So 10 digits make all the numbers, right? From 0 to 9, right? There's 10 digits. So, right, so 5-digit zip code. So I like to go like this, guys. It'll be this is my 1, right? My first digit, second, third, fourth, and fifth. So how many digits can go here, right? So there's 10. Because for the first part, there's no restrictions. How many zip codes are possible if there are no restrictions on the digits used? So 5-digit zip code, so 10 can go there, 10 can go there, and 10, and 10, and 10. You multiply it out, you get 100,000. Okay, now for part 2. The first one cannot be a 0, right? So if it cannot be a 0, it can be digits 1 through 9, so it's going to be 9, right? And then the rest have no restriction. So it can be 10, 10, 10, and 10. You multiply it out, and you get something like 90,000. Number 30, for how many years, for many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. So then, okay, so no, 26 letters are in the alphabet and 10 digits make the numbers. So how many different plates are possible with this arrangement? So the first 3, right, the first 3 are going to be what? Are going to be letters. And the next 3 are going to be numbers or digits. So how many letters are in the alphabet? 26, right? So 26 letters can go on the first slot, 26 there, 26 also on the third slot, 10 digits there, 10 and 10. You multiply it out and you get your answer. 17,576,000 different ways. So, hey guys, I bet when they first started making cars, right, because every car has to have a license plate. So the more cars that they make, they can add another digit or another letter to give you more numbers. I mean more cars. You know, for example, let's do part B. When the state ran out of new numbers, right, because they were making more cars, the order was reversed to 3 digits followed by 3 letters. How many new license plates were possible? So now they reverse the order. So these are the digits and these are the numbers, the letters. So 10 and 10, right? So 10 can go in the first space, 10 can go in the second, and 10 can go in the third. Same thing with the letters. In other words, same number of numbers, right? Because here you're applying the commutative property. If you reverse the order of when you multiply, you get the same answer. For part C, several years ago, the number described in part B were also used up. Then the state issued a plate with 1 letter followed by 3 digits and then 3 letters. How many new license plates were possible? So my first one's what is a letter, right? And then 3 digits and then 3 letters again. So 26, and then for the next 3 slots, it's going to be 10. And then it's going to be 26, 26, 26. You multiply it out, and that's your result. 556,976,000. Okay. We'll move down here, guys. So now comes the n factorial. N factorial means that you're going to be decreasing by 1 until you get to 1. For example, if you have n factorial means n, and then times n minus 1, times n minus 2, and so forth until you get to 3, 2, and 1. 0 factorial is equal to 1. Checkpoint. Find 4 factorial. It'll just be 4 times 3 times 2 times 1. You multiply them out, and you get 24. For B, 6 factorial, right? So it's going to be 6 times 5 times 4 times 3 times 2 times 1. You multiply all those digits, and you're going to get 720. For C, 1 factorial is equal to 1. For D, 6 factorial divided by 4 factorial. So 6 factorial will be the same thing as 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is the same thing as 4 times 3 times 2 times 1, right? So 1 divided by 1. So these are the same thing as 1. Same thing as 1. Same thing as 1. Same thing as 1, right? So these actually, you can say they cancel, right? Or all this is equal to 1. So 6 times 5 is 30. 30 times 5 is, 30 times 1 is 30. Now comes permutation. A permutation of set of elements is an ordering of the element. For instance, there are 6 permutations ordering the letters A, B, and C. These are all the possible ways you can name the letters in different order. Hey guys, here guys, the order matters. Okay, the order matters. For example, A, B, and C is the same thing as C, B, and A. It's different than C, B, and A. These are two different orders. This is crucial, guys, because for permutation, the order matters, and for combination, the order does not matter. Example, how many batting orders are possible for a 9-person baseball team? There are 9 possible choices, right? And then even so forth. So it's going to be 9 times 8, right? Or it's going to be 9 factorial, which is 362,880. The number of permutations of n elements is n factorial, right? Now, this is another formula, permutations. This is a formula. It's called NPR. It's equal to n factorial over parentheses n minus r plus parentheses factorial. Here, the order matters. Example, I have three letters, right? A, B, and C. I would like to know how many two-letter arrangements are possible. So the order is right. So this is the order A and B, or it can be B and A. It can be AC, CA, or BC and CB. These are all the possible combinations, right? Because the order matters. If you want to use a formula, right, so it's going to be 3 permutation 2, which means, right, this is my N, this is my R, so it's going to be 3 factorial over 3 minus 2 factorial. Right, 3 minus 2 is 1, so the answer is going to be 3 times 2 times 1 over 1. The answer will be 6, right? Same answer. Or you have 3 letters and one arrangements of 2, right? So this can be, right, so we have 3 letters, right? So you want 2 arrangements, so it can be 3 times 2. That's your answer. So this has different ways to get the answer on this one. This is number 40 from page 478. From a cooler with 8 cans of different kinds of sodas, 3 are selected for 3 people. In how many ways can this be done? Right? So there's 8. You want to select them for 3 at a time. So it's going to be 8 permutation 3. This can also be put in the calculator, guys, but I like to show you by hand also. So 8 factorial would just be 8 times 5 times 6 times 5 factorial. Why did I stop here? Because I don't want to continue, guys, because I don't want to do extra work. So 8 minus 3, right, is factorial is 5 factorial, so these will cancel out to 1. So 8 times 7 times 6 is 336. Or, right, you have 8 cans and one arrangement 3 at a time, so you're going to put 3 like that, 1, 2, 3, right? How many can go here? It's going to be 8, and then 7, and then 6. You multiply them out, you get the same answer. So this has 2 ways to get the answer, guys. Now, combination is different. For combination, the order does not matter, okay? Remember those 3 letters, guys, that we wanted to put them in groups of 2s? It can be AB, it can be AC, or it can be BC, because AB and BA are the same thing, right? Because order does not matter. So now let's use the formula. So 3 combination 2 is going to be 3 factorial over 2 factorial minus 3 minus 2 factorial. So I get 3 factorial will give us 3 times 2 times 1. The 2 factorial is going to give me 2 times 1. 1 factorial will give me 1, right? So the answer will just be 3. Okay. This is number 46 from 478. 4 items are to be randomly selected from the first 25 items on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? So it's going to be 25, combination 4. Okay. And again, this can be put in the calculator to get the answer, but this is how you do it by hand. Why did I stop at 21? So I can cancel the 21 on the bottom. And the 4 factorial will give us 4 times 3 times 2, right? So 4 times 3 times 2 times 1, right, will give us 24. 4 times 3 is 12, times 2 is 24, so that cancels with that one there. So I'm left with 25 times 23 times 22. That's your result. Okay, now, guys, I believe I have 2 more slides, guys, and that's it. So this is the rule for permutations and combinations. And these are always the key words that tells you going to be a permutation. If it says arrangement, schedule, order matters. The clue words for combinations are groups, committee, set, samples. Order does not matter. Okay. So those are good to know. This is number 59 from page 478. A lottery game requires that you pick 6 different. I forgot to put numbers there, from 1 to 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 numbers if order is not important, right? So this is going to be a combination, right? Because the order is not important, right? Not important, so it's going to be a combination. So how many are there? 99 numbers, right? So it's going to be 99 combination 6, and that's your answer. 1,120,429,256. For B part, right? The order matters, so that's going to be a permutation. And the answer is even more than that. Okay, that's your answer. Okay, now, I believe I have two more problems to be done here. It says here, in exercise, this is number 60, page 479. In exercise 59, if you pick 5 out of 6 numbers correctly, you win $5,000. In how many ways can you pick exactly 5 out of 6 winning numbers without regards to order? So here, guys, is going to be a combination, right? So here's my solution. So first, you want to get 5 out of the 6 winning numbers right to win the 5,000. So it's going to be 6 combination 5. Because from the 6 numbers, you have to get 5 correctly to win the 5,000. And then times right. Remember, the lottery requires need to pick 6 numbers, right? So then, from the right, if there was 99 numbers, right? So if there's 6 already shown in here, how many are left? 93 are left. So for the 93 other numbers, you need to pick 1. So with 93 combination 1. You multiply them out, right? And you get your answer. If you notice, these, the first, the ends, right? The NCR, the ends must equal to 99 because there's 99 numbers. And the R, it has to be 6 because you have to choose 6 numbers. So that's why this is my how you're going to solve this problem here. So 6 combination 5 is equal to 6 times 93 combination 1 is equal to 93. You multiply it out. So that's your answer, guys. 558. Now, this is the last one here, I believe. Number 58 from page 479. A financial advisor offers 8 mutual funds in the high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest 3 at the high risk funds, 4 moderate risk funds, and 3 at the low risk funds. How many ways can the investor do this? Okay, so let's get the information here. So this will be combination here, right? So from the 8, I want to pick, right, from the 8 that are high risk, I want to pick 3. So it's going to be 8 combination 3. And then from the moderate risk, right, from 7 moderate risk, I have to pick 4. So it's going to be 7 combination 4. And for the low risk, it's going to be, if there's 10, right, and I want to get 3. So it's going to be 10 combination 3. So 8 combination 3 will give you 56. 7 combination 4 will give you 35. And 10 combination 3 will give you 120. You multiply them all out. And the answer is 235,200. Okay. So that's how many ways the funds can be selected. Hey guys, thank you guys, and I'm sorry for going half an hour over, but I truly believe this was important because this is a mini master. But I apologize for going over, guys, and sorry to the other moderates that I took 30 minutes out of the time. Anyway, guys, do you have any questions?
Thank you, Mr. Azasi. Does anyone have any questions for Mr. Azasi before we wrap up? Okay. I would like to thank you, Mr. Azasi, for presenting for us and then doing such a thorough job. I really do appreciate it. I know the students do. Della says it was informative and needed, and Peter gives you a thumbs up, and Tim gives you a great presentation.
Thank you, guys.
Thank you. So before I let you guys go, I'm going to invite you to this Friday's presentation. Give me just a second. Friday. Okay, so today's session was sets, concepts, probability, and permutations and combinations. And on Friday, July 2nd at 3 p.m., we'll be having synthetic division and finding zeros. And then just a quick reminder that next Monday, we won't be having a TBE due to the institutional holiday, but we'll be back here next week, July 9th at 3 p.m. Thank you for coming today, and y'all have been a wonderful audience. And thank you again to Mr. Azasi for your wonderful presentation.